This is third and last module of chapter 1. In this module, we shall introduce different type of operators which are used in numerical analysis. The most useful operators are forward difference operator, backward difference operator, central difference operator, and these operators are also known as finite difference operator, and other operators are shift operators, average operators, differential operators, and so on. So, the forward difference operator and shift operator are used to construct the difference equations which are used in discrete mathematics, and this equation is similar to differential equations. So, in this module we shall discuss about these types of operators, their properties and their interrelationship and their applications to solve different problems in numerical analysis. First we define forward difference operator, and that operator is denoted by capital delta and is defined by capital delta f of x equal to f of x plus h minus f x. When x equal to x I, then the above equation becomes delta f of x I equal to f of x I plus h minus f of x I, that is in terms of ordinate this becomes delta y I equal to y I plus 1 minus y I, and this is true for all I equal to 0 to n minus 1, that is this is true for n values. In particular, delta y 0 equal to y 1 minus y 0, delta y 1 equal to y 2 minus y 1, and so on. These are called the first order differences. Similarly, the second order differences are obtained by delta 2 y 0 equal to delta y 1 minus delta y 0, that means by taking the first difference of y 1 and y 0, and after simplification this equation becomes y 2 minus 2 y 1 plus y 0. Similarly, delta 2 y 1 equal to y 3 minus 2 y 2 plus y 1, and for third order differences delta 3 y 0 equal to after simplification y 3 minus 3 y 2 plus 3 y 1 minus y 0, and delta 3 y 1 equal to y 4 minus 3 y 3 plus 3 y 2 minus y 1. In general, delta power n plus 1 f of x equal to delta of delta n f of x, that is in terms of ordinate this becomes delta power n plus 1 y I equal to delta of delta n y I, and this is true for all n equal to 0, 1, 2 and so on. In particular, delta 0 represents the identity operator, that means delta 0 f x equal to f x, and delta 1 is equivalent to the operator delta. Let x 0, x 1 to x 4 be 5 arguments, that means the values of x. For this set of values of x, we construct a difference table. This is called the forward difference table or diagonal difference table. The first column of this table represents the values of x, second column represents the values of y, and third column represents the values of the first order differences, and so on. Now, the forward difference operator satisfied many interesting properties. Some of them are presented in this slide. The first order difference of any constant c is equal to 0. The differences of the sum of n functions equal to the sum of the differences of the functions. Third one is the difference of c into f x equal to c into delta f x, where c is any constant, that means there is no effect on the constant c for the forward differences. And the condition 4 is delta of c 1 f 1 x plus c 2 f 2 x plus dot 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 plus c n f n x equal to c 1 delta f 1 x plus c 2 delta f 2 x plus dot 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 plus c n delta f of x n. This is similar to the linear operator, that means we can say that the forward difference operator is a linear operator. The forward difference operator also satisfies the laws of indices, that means delta power m into delta power n f x equal to delta power m plus n f x, which is equal to delta power n into delta power n f x, and this is equal to delta power k into delta power m plus n minus k of f x, and this is true for any k equal to 0 to 1 up to m or n. And the next property is the delta of c to the power x, where c is a constant. This is equal to c to the power x plus h minus c to the power x, and which is equal to c to the power x into c to the power h minus 1, and this relation is true for any constant c. Let us consider one example to describe the nature of the forward difference operator. The forward difference operator of f x by g x is equal to g x into delta of f x minus f x into delta of g x whole divided by g of x plus h into g x, provided g x not equal to 0. If it is equal to 0, then the entire thing is undefined. Now, we prove this result in the following lines. Delta of f x by g x equal to f of x plus h by g of x plus h minus f x by g x as per definition of forward difference operator. And after simplification, this expression becomes f of x plus h into g x minus g of x plus h into f of x by g of x plus h into g x, and after simplification lastly we get g x into delta of f x minus f x into delta of g x whole divided by g of x plus h into g x. So, this is the result of forward difference operator on the division of two functions. Now, we define another important forward difference operator called the backward difference operator. The backward difference operator is denoted by the symbol nabla. The definition is nabla of f x equal to f x minus f of x minus h, and in terms of ordinate this equation reduces to nabla y I equal to y I minus y I minus 1. This is called the first order backward difference operator, and this is true for a I equal to n minus 1 up to 1. Similarly, we can define or deduce the other differences, first order differences, say nabla y 1 equal to y 1 minus y 0, nabla y 2 equal to y 2 minus y 1, and lastly nabla y n equal to y n minus y n minus 1. So, these are the first order backward differences. The higher order backward differences are also defined here. Nabla 2 y 2 equal to y 2 minus 2 y 1 plus y 0, and this is nothing but delta 2 y 0, and nabla 2 y 3 equal to y 3 minus 2 y 2 plus y 1, this is equal to delta 2 y 1, and delta 2 y 4 equal to y 4 minus 2 y 3 plus y 2. In general, nabla k y I equal to nabla k minus y I minus nabla k minus 1 y I minus I, and this is true for I equal to n minus 1 up to k. In particular, nabla 0 y I equal to y I, because nabla 0 is the identity operator, and nabla 1 y I equal to nabla y I. Like forward difference table, we can generate the backward difference table. In this table, the first column represents the arguments, the values of x, second column represents the values of y, and third column represents all order first order backward differences, fourth column represents all second order backward differences, and so on. This table is also known as backward difference table or horizontal table. Now, we come to another finite difference operator known as central difference operator, and this operator is denoted by small delta. It may be noted that the forward difference operator is denoted by capital delta, but central difference operator is denoted by small delta. The small delta of f x equal to f of x plus h by 2 minus f of x minus h by 2. Note that in this case x is the middle point, and h by 2 and minus h by 2 represents the right hand and left hand length of the point from the middle position x, and it also noted that the length of the interval is h. In terms of ordinate, that means when x equal to x I, this expression becomes delta y I equal to y I plus half minus y I minus half. Also, y I plus half equal to f of x I plus h by 2, and y I minus half equal to f of x I minus h by 2. So, this is the central difference operator in terms of ordinate. In particular, delta y half equal to y 1 minus y 0, delta y 3 by 2 equal to y 2 minus y 1, and so on. Similarly, the second order central differences are defined as follows: delta 2 y I equal to y I plus 1 minus 2 y I plus y I minus 1. In general, delta n y I equal to delta n minus 1 y I plus half minus delta n minus 1 y I minus half. This is the general expression to find the any order central differences for the ordinate y 0, y 1 up to y n. Now, I come to another type of operator, very useful operator, that one is called the shift operator, and the shift operator is denoted by capital E, and which is defined by E of f x equal to f of x plus h. And in terms of y, this formula becomes E y I equal to y I plus 1. Note that the shift operator actually increase the subscript of y by 1. So, that is why it is called the shift operator, and when the shift operator is applied twice on a function, then this is actually increase the subscript of y by 2 unit at a time. That means, e to f x equal to e of f x, and after simplification this becomes f of x plus 2h. That means, e to f x equal to f of x plus twice h. In general, we can write e to the power n of f x equal to f of x plus n h, and we shall also define another operator called the inverse shift operator. That one is denoted by e to the power minus 1 and defined by e to the power minus 1 f x equal to f of x minus h, and second order inverse shift operator is denoted by e to the power minus 2 and which is defined by e to the power minus 2 f x equal to f of x minus twice h, and in general e to the power minus n f x equal to f of x minus n h. In general, the most general expression is e to the power r f x equal to f of x plus r h, or in terms of ordinate e to the power r y I equal to y I plus r h, where r is any positive as well as negative integer or rational numbers. Like forward difference operator, the shift operator also satisfied very many interesting properties. The first one is the E of c, where c is any constant, E of c equal to c, that means it remains unchanged. Again, E of c of f x equal to c of E of f x, that means there is no effect of shift operator on the constant c. Third property is this one. The third property indicates that the shift operator is linear, that means E of c 1 f 1 x plus c 2 f 2 x plus up to c n f n x is equal to c 1 E f 1 x plus c 2 E f 2 x up to c n E f n x. So, actually this is nothing but the linear property of any operator. Also, the shift operator satisfy the laws of indices like forward difference operator, that means e to the power m into e to the power n f x equal to E n E m f x equal to E of m plus n f x. And the fifth operator very interesting, E n E minus n f x equal to f x, that means E n E of minus n is nothing but the identity operator. And the next property is that E of n power m of f x equal to e to the power m n f x. The shift operator can be applied to the division of two functions, and the property gives E of f x by g x equal to E of f x by E of g x, but this property does not hold for forward difference operator and backward difference operator. This one only valid for the shift operator. And the shift operator for the product of two functions is given in property 8. The E of f x into g x is equal to E of f x into E of Gx. So, these are the few important properties of shift operator. Now, we shall define average operator, that one denoted by mu. So, mu of f x equal to half of f of x plus h by 2 plus f of x minus h by 2. Actually, this is actually computes the average of two functional values. That is why it is called the average operator, and in terms of ordinate, this expression becomes mu of y I equal to half of y I plus half plus y I minus half. Now, we define the differential operator, that one denoted by capital D, and this is well known operator which is used in differential calculus. The capital D of f x equal to derivative of f x, that one also denoted by f dash x, and second derivative, that means capital D 2 f x equal to second derivative of f x, that one equal to f double dash of x, and in general d n f x equal to nth order derivative of f x, which is equal to f n f x. So, we have defined 6 different operators, but there are many interesting relations among this operator. We shall present here some important relationship among the forward difference operator, backward difference operator and other operators. First, we consider the forward difference operator delta y I, which is equal to y I plus 1 minus y I, that one equal to nabla y I plus 1, which is equal to small delta y I plus half as by definition of central difference operator. Similarly, for second order difference, delta 2 y I equal to y I plus 2 minus 2 y I plus 1 plus y I equal to nabla 2 y I plus 2, which is equal to small delta 2 y I plus 1. In general, we can show that delta n y I equal to nabla n y I plus n, where I equal to n integers say 0, 1, 2 and so on. And there is a very interesting relation between the shift operator E and the forward difference operator delta, which is obtained in the following line. Delta f x equal to f of x plus h minus f x, and the first term is nothing but E of f x minus f x, and then this is equal to E minus 1 f x. That means, we see that delta operator and E minus 1 operator are equivalent. That is, we can write delta equivalent to E minus 1, or after rearranging we can write E equal to delta plus 1. So, these are the relation between the shift operator and forward difference operator. Similarly, we can derive a relation between nabla operator and E operator, that means backward difference operator and shift operator. Now, the backward difference operator nabla of f x equal to f x minus f of x minus h equal to f x minus e to the power minus 1 f x as by definition of e to the power minus 1, the inverse shift operator, which is equal to 1 minus e to the power minus 1 whole into f x. That means, the nabla is equivalent to 1 minus e to the power minus 1. Or also we can write e to the power minus 1 equal to 1 minus nabla. So, this is the relation between the backward difference operator and shift operator. Now, for third order forward difference operator, that means delta 3 y I equal to E minus 1 power 3 y I. After simplification, this expression is reduces to y 3 minus 3 y 2 plus 3 y 1 minus y 0. In terms of central difference operator small delta, the delta f x equal to f of x plus h minus f of x minus h, and in terms of shift operator, this expression becomes e to the power half f x minus e to the power minus half f x, and it is equal to e to the power half minus e to the power minus half whole into f x. That means, the central difference operator is equivalent to e to the power half minus e to the power minus half. This is the relation between central difference operator and shift operator E. Similarly, we can derive the relation between the average operator in terms of shift operator, in terms of central difference operator. like this. So, mu of f x equal to half of f of x plus h by 2 plus f of x minus h by 2, and in terms of shift operator, the first term is e to the power half f x and second term is e to the power minus half f x. So, it is equal to half of e to the power half plus e to the power minus half whole into f x. Therefore, mu is equivalent to half of e to the power half plus e to the power minus half. So, this is a relation between average operator and the shift operator u. In case of second order average operator, that means mu to f x equal to 1/4 e to the power half plus e to the power minus half power 2 f x. After simplification, this expression reduces to 1 by 4 delta 2 plus 4 into f x. That means mu 2 equivalent to 1 by 4 delta square plus 4, or this is nothing but mu is equivalent to square root of 1 plus 1 by 4 delta 2. There is a very interesting relation between the shift operator and the differential operator, that one deduced in this slide. E of f x equal to f of x plus h, and by Taylor series we know that f of x plus h is equal to f x plus h into f dash x, that means the first derivative, plus h square by factorial 2 into second derivative of f x, and so on. So, using the differential operator d, this expression becomes f x plus h d of f x plus h square by factorial 2 delta 2 f x plus h cube by factorial 3 delta 3 f x, and so on. After taken common f x, we obtain 1 plus h d plus h square by factorial 2 d 2 plus h cube by factorial 3 d 3, and so on, whole into f of x. So, note that the expression within the bracket, within the square bracket, represents e to the power h d. That means E is equivalent to e to the power h d. So, this is a very nice relationship between the shift operator and the differential operator in terms of E. This expression can also be written as h d equal to log of E. The log means the ordinary log whose base is E. Now, this slide actually gives the relationship between the operators which are discussed in this module, and here we shown that each operator can be expressed in terms of other operators. The first line shows that the operator E can be written in terms of forward difference operator delta, and we say that E is equivalent to delta plus 1, this one already proved in previous slide, and E also can express in terms of the backward difference operator, and that one is equivalent to 1 minus nabla whole power minus 1. E is equal to 1 plus delta 2 by 2 plus delta into root over 1 plus delta square by 4. That means E can be expressed in terms of central difference operator, and we have proved that the shift operator E is equivalent to e to the power h d. That means the operator E, that means the shift operator, can be expressed in terms of other operators. Similarly, in second row we have shown that the forward difference operator can be expressed in terms of other operator like shift operator, backward difference operator, central difference operator, and differential operator, and this is true for other operators. So, from this table we can conclude that the operators, the 6 operators discussed in this module, are not independent. One operator can depends on other operators. So, we have defined 6 important and useful operators which are used in numerical analysis. Now, we shall introduce one important notation called the factorial power notation. If a polynomial can be expressed in terms of factorial power notation, then we can determine the first order difference, first order forward difference or first order backward difference of a polynomial using the same rules which are used in differential calculus, in particular the rules used in derivatives. So, factorial power notation is a very powerful notation, and the different order difference of a polynomial are used in difference equations which are used in discrete mathematics. So, in this slide we shall show that the forward difference operator is equivalent to the differential operator if the step length h is very small. To prove it, we shall consider the definition of derivative, that means f dash x equal to limit h tends to 0 f of x plus h minus f x whole divided by h. This is the fundamental definition of derivative, and this is equal to limit h tends to 0 and the numerator is equal to delta f x by h. That means, if we assume that h is very small, that means tends to 0, then delta f x is approximately equal to h into f dash x equal to h d f x. That means, delta is equivalent to h d in case of small h. Similarly, for second order derivative f double dash x equal to limit h tends to 0 delta to f x by h square. Hence, delta to f x equivalent to delta to f double dash x equal to h square d square f x. That means, delta 2 is equivalent to h square d square provided h is very small. In general, we show that delta n is equivalent to h to the power n d to the power n for small h. Now, we come to the factorial power notation, that one we have mentioned just few minutes back. The nth factorial of x is denoted by x power bracket n and is defined by x power factorial n equal to x into x minus h into x minus 2h up to x minus n minus 1h. That means, right hand side contains n factors, that is why the power is denoted by n. So, here we have denoted the parenthesis to represent the factorial power notation, but some author denotes the square bracket instead of the parenthesis. So, in particularly when n equal to 0, the x power factorial 0 is equal to 1. Similarly, for negative integer or for negative n, we can define the factorial power of x like this: x factorial minus n equal to 1 by x into x plus h into x plus twice h dot 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 x plus n minus 1 into h. But it is very interesting that x factorial n into x factorial minus n is not equal to 1. That means, x factorial n is not the inverse of x factorial minus n with respect to ordinary multiplication. Now, some particular cases of factorial power notation are defined here: x power 0 equal to 1, x power factorial 1 equal to x power factorial 2 equal to x into x minus h, and so on. Conversely, we can write this expression as 1 equal to x factorial power 0, x equal to x factorial power 1, x square equal to x factorial power 2 plus h into x factorial power 1, x cube equal to x factorial 3 plus 3h x factorial power 2 plus h square x factorial power 1, and so on. That means, any polynomial can be expressed in terms of factorial power notation, and note that the degree of the polynomial remains same or unchanged under this transformation. So, we have noted these remarks. The degree of x to the power k for any k remains unchanged while expressed it in factorial notation. So, from this observation, we can state the following lemma: any polynomial f x in x can be expressed in factorial notation with same degree. Now, we consider one example. Here we consider f x equal to 10 x to the power 4 minus 41 x to the power 3 plus 4 x to the power 2 plus 3 x plus 7. Our problem is to express this expression in terms of factorial notation and also find its first and second differences. So, for simplicity, we assume that h equal to 1, then x equal to x factorial 1, x square equal to x factorial 2 plus x factorial 1, and x cube equal to x factorial 3 plus 3 x factorial 2 plus x factorial 1, and so on. So, by substituting all these values x, x square, x cube and x 4 in terms of factorial notation, the given function f x becomes 10 into x factorial 4 plus 19 into x factorial 3 minus 49 into x factorial 2 minus 24 into x factorial 1 plus 7. So, this is the f(x) in terms of factorial power notation, and note that the degree of the original function f(x) was 4, and in terms of factorial notation the degree remains unchanged, that one is 4. Again we know that delta x factorial n equal to n x factorial n minus 1. This relation actually is similar to the rules of derivative. So, using this result, we consider or we determine the first order difference of f(x), say delta f(x), which is equal to 10 into x factorial 4 becomes 4 into x factorial 3. The second term 19 x to the power factorial 3, that becomes 19 into 3 x to the power factorial 2 minus 49 into 2 into x to the power factorial 1 minus 24 into 1 factorial power 0. After simplification, this becomes 40 x factorial power 3 plus 57 x factorial power 2 minus 98 x factorial power 1 minus 24. And in terms of x, this becomes 40x cube minus 63x square minus 75x minus 24. So, this is the first order difference of f(x), and this is very simple expression, and it is obtained by the rules used in derivatives. Similarly, delta to f(x) equal to 120 x factorial 2 plus 114 x factorial 1 minus 98. After simplification in terms of x, this becomes 120 x square minus 6x minus 98. So, we observe that in terms of factorial notation, the differences are easily calculated using the rules of derivatives. Now, let us consider one important and interesting problem, that means the difference of a polynomial, and this is used in many places of numerical analysis. Let us consider f(x) equal to a0 x to the power n plus a1 x to the power n minus 1 up to a n minus 1 x plus n, and this is a polynomial of degree n, and in terms of factorial notation, this function can be written as, this polynomial can be written as b0 x factorial power n plus b1 x factorial power n minus 1 plus b2 into x factorial power n minus 2 and so on. Lastly, bn minus 1 x to the power factorial 1 plus bn, and the degree of the polynomial remains unchanged, but the coefficient b0, b1, b2 etc. can be represented in terms of a. There is some rules are available. Now, we find the first order difference of f(x). The first order difference of f(x) equal to b0 n h x to the power factorial n minus 1, b1 h n minus 1 factorial n minus 2 and so on. The last term becomes bn minus 1 h. Here we have taken h is the spacing between the values of x. Clearly, this is a polynomial of degree n minus 1. Now, it take the second order differences using the same rules, and second order difference of f(x) is equal to b0 n into n minus 1 h square factorial n minus 2 plus b1 n minus 1 into n minus 2 h square x to the power factorial n minus 3 and so on. And note that this is a polynomial of degree n minus 2, and third order difference delta 3 f(x) equal to b0 n minus 1 n minus 2 h cube into x factorial n minus 3 and so on. The last term is b n minus 3 h cube. So, in this way we obtain delta k f(x) equal to b0 n minus 1 n minus 2 up to n minus k plus 1 into h to the power k x to the power n minus k. Thus, finally, we conclude that delta power k f(x) when k is less than n is the degree of the polynomial. So, delta k f(x) is a polynomial of degree n minus k. Delta n f(x) equal to b0 factorial n h to the power n, and which is equal to factorial n h to the power n a0. This is a constant, and when k greater than n, delta k f(x) equal to 0, which is obvious because the difference of any constant is 0. In particular, delta n plus 1 f(x) equal to 0. So, we have shown that the n order forward difference of a polynomial of degree n is a constant, and higher order derivative of the same polynomial is equal to 0, and lower order difference of the same polynomial is a polynomial of degree say n minus k if we take the kth order difference. This is the last module of chapter 1. In chapter 1 we have discussed the different kinds of errors, their sources and their effect we have discussed in module 1 and module 2 of this chapter. And in this chapter, that means the third chapter, we have discussed different types of operators which are used in different chapter of numerical analysis, and we have defined these operators, their properties we have investigated, and we have introduced the relationship between the operators in terms of one operators in terms of other operators, and we have also introduced the factorial power notation, and this factorial power notation is used to find out the different order differences of a polynomial, and this difference is useful to find or to solve the difference equations which are widely used in numerical mathematics. So, with these few words I finish the chapter 1.